Early effect and BJT characteristics. Why I have combined these two topics are: early effect has a greater link to characteristics because early effect will develop equations for characteristics, and the characteristics will give us explanation of the behavior. Let's go for introductory words. Starting with diode. One basic concept is linked in BJT as well as FET from the diode is step graded junction. Look at here. This is heavily doped. This is N. If you reverse bias, number of ions are same, but this is have less width, this has more width. So less width to more width is here. When the width is less, height is more. When the width is more, height is less. That's why area under the curve is same, but the width is more on the lightly doped side. This is for unequally doped. We call it as step graded or abrupt junction. Why this is called step graded? Because it is looking like step here. That's why when a PN diode is connected in reverse bias, junction width is increased more in lightly doped region. Similarly, in BJT, when the collector junction is reverse biased, junction width at the collector increases, but the increase is more into base side. By that, base width changes or decreases. When the base width is decreasing, we call it as base width modulation or early effect. So this is the key point for our characteristics. Let's see early effect or base width modulation. Look at the dotted line. Dotted line is basically open circuit conditions. Under open circuit conditions, cut-in voltages are approximately equal. In the process, what happens is, now you forward bias the input junction. When you forward bias the junction width decrease. That's why it is gone from here to here. This is decreased. Whereas at the output side, it is increased because we are reverse biasing this. When you reverse bias this, voltage increase. It's not only voltage increase, it is junction width increase. So when the junction width increases, you know what is happening? When the junction width is increasing, but more into lightly doped. Lightly doped is base. That's why I said P minus, N plus, P minus, more into this. So base width is effectively decreased. That's why it is called base width modulation. Modulation means decreased. Okay. Let me talk to you about what exactly happening, some conclusions. First, under open circuit condition, junction potential is almost same, equal to cut-in voltage. When I forward bias VAB at the input, VAB decreases, and hence junction width also decrease. When I reverse bias, VCB increase, and hence junction width also increase, but more into the base because base is lightly doped. Fourth, as V0 increases, junction width Vj also increase and base width decrease. Therefore, it's called base width modulation. As V0 further increase, Vj further decrease. At one point, the junction width becomes, base width becomes 0. When the base width becomes 0, it's almost like saying emitter and collector get shorted. Emitter is N and collector is also N. That means N and N became a single material when base disappears. Suppose in NPN transistor, if base is disappeared or completely 0, it becomes semiconductor material. That's what I mean. So what to do? You have to use voltage very lesser than breakdown. That's called actually breakdown voltage. Breakdown voltage is a voltage at which punch through occurs. Or punch through means base width becomes 0. So what to do is, take lesser than VC. VCC take half of BVCO. And generally VC is half of VCC by 8. Therefore, the voltage that you are taking is almost 1/4 of the breakdown. For example, your breakdown voltage is 40. 40 by 4 is 10. That's why roughly take 10. Or less than 10 is also better. That's why we normally operate at 6 volts or 5 volts. So this is how we have to choose the values of VCE depending on a breakdown voltage. Let me talk to you by taking an example. VCC is 12 and then VC is 6. Then what's the breakdown voltage? If IB is 0, IC is 0, then VCC comes here. The total VCC comes here. Then there is a chance of breakdown because maximum voltage is coming. But if IB is not 0 and this is 0, if IB is not 0, IC not 0, therefore there is a drop. This voltage will be less than VCC. It will not break. The whole idea that I am trying to say is breakdown is generally linked to open circuit of input. That's the meaning. So BVCBO is common base with emitter open. That's the voltage between collector and base emitter open. Whereas BVCO is a voltage between collector and emitter base open. O means open circuit. That's why generally breakdown voltage is linked with input open circuit. But one observation we all know, even in the previous lecture I told you, BVCBO is greater than or equal to 4 times of BVCO. That means common base can bear something more than common emitter configuration. If V0 is much more increase and increase, at one point base width decrease and decrease, it becomes 0. That is called punch through or breakdown. Sixth point, as V0 further increase, base width further decreases, and when the base width decrease, carriers can easily go into output. That's why I0 increases. Therefore, I0 is function of V0. And we already know IC equal to beta times of IB. Therefore, I0 is IC is input depending on input. So I0 is depending on input, I0 is depending on output. If you combine, I0 is function of IA and V0. Therefore, BJT is called current control device. Look at this point here. This is input current, output voltage. But control is generally from input. That's why this current is controlling output. That's why it's called current control device. Suppose if you take BJT, input current is not 0, therefore power dissipation is high. Whereas in FET, input current is 0, therefore power dissipation is less or approximately 0. And why I'm saying approximately 0, because input power is anyway 0, but there can be output power now. That's why I'm saying approximately 0 but not 0. But one way, in terms of power dissipation, FET is better. Then the seventh point, as output voltage increases, minority carriers of the base are attracted. When the output voltage increase, minority carriers of the base are attracted. For example, when you increase output voltage from positive because reverse bias, the minority carriers of base means electrons get attracted. When they get attracted, it is empty itself. Therefore, a new concentration gradient is created between emitter to base. When the new concentration is created between emitter and base, you know what happens? Current increases. When the current is increasing, that means opposition is decreasing. Therefore, input voltage get decreased. Finally, what is got affected? Input voltage. Because of what? Output voltage. So, output voltage is really function of input voltage. Therefore, VI is function of I0. If I conclude this, VI is function of V0, IA is anyway already taken. I0 is function of IA and V0. These are the two characteristic equations that are taken. And listen here, this is VI, this is IA. Two things belongs to input, therefore this should be called as, from now onwards, input characteristic equation. I0, function of V0, and two things belong to output, it is called output characteristic equation. So input characteristic equation and output characteristic equations, two equations we have developed based on early effect. Therefore, the very purpose of early effect is to develop these two equations in order to draw characteristics. You know why? When you are trying to draw the characteristics, you will have a question saying which one to be taken on x-axis, what to be taken on y-axis. And that can be given only by what you call characteristic equation. So having characteristic equation, I am going to draw the characteristics now. So let's start with common base characteristics. When I say characteristics, there are three characteristics: common base, base as a common, base as emitter, common base, common emitter, common collector. So BJT generally works in active mode for forward. If you go for forward bias and reverse bias at the output, forward bias at input, reverse bias at output is called active mode. So we are going to bias for that. And look at the bias here. N is given to N, forward bias. N is given to P, reverse bias. And these two are variables here. And input current is IE, output current is IC. Now what are the functions here? Look at the input equation. VEB is function of IE, VCB. IC is function of IE and VCB. So this IC is affected by the voltage as well as input. Please understand, output is affected by the input and input is affected by the output. That is what actually transistor is talking about. That's the beauty of the transistor. It's all because of these two equations. You see, input is affected by output. Output is affected by input. Therefore, when you're drawing characteristics, these are the basics. Now let me give you the output characteristics. IC is function of IE and VCB. That means the output elements are IC and VCB. Then what happens to IE? IE becomes a fixed value. So fix IE, vary VCB, note down IC. How do we fix IE? By varying input supply, fix IE and then vary this. That's called characteristics here. So IE is equal to 1, VCB versus IC. I equal to 2, VCB versus IC. IB has to be fixed by changing VE. An increase in VCB is affecting to decrease the base width. IE may be changing at every time because of VCB. That's early effect. As output voltage is changing, input is also changing. That's why there is every chance for IE that is fluctuating. That's why make sure for every reading of IE, you need to take input current. You need to ensure that the input current is maintained constant. That is the meaning of maintaining IE. Therefore, if you really don't maintain it, there is characteristics will not come. This problem is very much in common base only, because in common base the input impedance is low. When the input impedance is low, it can load even on the battery. I have seen personally in the laboratory, as output voltage is increasing, to draw the characteristics, input supply is also loaded and IE is always getting affected. Therefore, always keep one ammeter to read this IE and see that it is always maintained constant. What I mean is, whenever loading effect takes place, IE going down. When IE is going down, you need to raise it by increasing the input supply. That's why whatever that you do it, but I am only telling, make sure that IE that is maintained as 1 milliampere to be at 1 milliampere for every reading of output in this table. Particularly in the laboratory, you need to be sure. VCB and IC, VCB and IC here. Therefore, if you draw the characteristics, what happens is here. And the very interesting, surprising thing is, the characteristic starts right even in the negative side. And most of the people, they really start from supply here. They suddenly see large current coming and maintaining constant. They don't see this portion of the curve. You know why? This portion of the curve they don't see because they are straight away giving a positive output voltage. So my suggestion is, for some time minus values you give to the output, then slowly it will raise, then you give positive. Normally nobody does it, that's why they don't see this portion of the curve. But if anybody is interested to see this portion of the curve, they should go from negative supply at the output, increase it to 0, that's actually saturation, then starts active. So the constant curve is coming, and most of the students are complaining me, they are telling me, sir, we are not getting this portion. They don't get it because they are starting from 0, that's why constant is coming. If they can start from negative side, they don't get on that side. They get the negative curve and then a constant here. So this is my suggestion for people who want to really see and observe, follow what I said. Now, this is forward bias because we are giving negative voltage. Negative voltage given to N is forward. And from here it is for reverse bias. Therefore, this can be saturation region and this is active region. Below, down the current, that is called cutoff. This is not cutoff. This dotted line is below 0 current, it is cutoff. And this is saturation, and remaining this portion is actually active region. This is during the active region, it is acting as amplifier. And you know, this curve is active region. It's called active region in BJT. The same constant characteristics is called pinch off in FET, JFET, and the same type of curve is called saturation in MOSFET. And but three different names people are confusing. Therefore, I said very simple word, constant current characteristics is a simple word for all the three. So for any device to act as an amplifier, it must possess constant current region. So tomorrow if you want to invent a new device, you are welcome, but you must show where the constant current is coming. Without constant current characteristics, it cannot be used as an amplifier. In fact, it cannot be a transistor. You know why it cannot be a transistor? Look at here. This is current is constant and voltage is increasing. When voltage is increasing, current is constant. What's happening inside? There's always a question saying, sir, what's happening and current is not changing? The very reason that the current is not changing, indirectly it says internally resistance is changing. What I mean is, when the voltage is increasing, current is not changing. That means resistance is changing from low to high. When the resistance is changing from low to high, we call it as transfer resistor, transistor. In fact, only in this region it is acting as a transistor. When it is acting as a transistor in that region, we really call it as transistor. So transistor is really behaving like a transistor in this region, and hence it is called active region. Active region is region where it is actually working what it is supposed to be. That's why this is called active region. In this region, it is acting as an amplifier. V0 is proportional to Vi, and the proportionality constant, we call it as linear region. Be careful, a constant current characteristics is called linear, not because there is a linear curve there. Actually, the linearity curve, if you really want to see it, is in terms of resistor. Because from your childhood, you know whatever to be called as linear, it should be increasing proportionally. Now, what is increasing proportionally here? It's not the current, it is the resistance is increasing, so it is called linear curve. So, transistor behaves like a linear element in this portion of constant current characteristics or active region. Whereas diode is almost everywhere is non-linear, but a transistor is acting as linear. So, in active region, I am defining output resistance, change in VB, change in voltage by change in current. For I is equal to 1 milli. What I mean is here, you look at here, I am taking change in this IC. It's very difficult, very less almost on this curve. For I is equal to 1, not difference of these two. It is two different values on this curve, very, very less. When IC is very, very less, what happens? Resistance is very, very high. So resistance is almost hundreds of kilo ohms in common base at output. And what about current gain here? Current gain you can calculate IC2 minus IC1 by IE2 minus IC1. If you observe these characteristics, 1.9 minus 0.9 by 2 minus 1, and then is approximately 1. That's why current gain is very small, less than or equal to 1. I know everybody is talking about voltage gain is less than or equal to 1 in common collector, but you should also know that current gain is less than or equal to 1 in common base. And this actually can be called as HFB, because forward current gain. That's how there is a possibility of calculating H parameters even from DC characteristics, because the moment you take a change here, even it can call it as output resistance. In fact, if you want to know HOB, output conductance, it is 1 by 100 kilo. So output conductance will come from here and the current gain will come from here. That's why there is always a exercise that you have to get H parameters right from the characteristics. So you don't need to wait till we go to AC parameters, because AC parameters can be achieved from DC parameters by taking a change. As I've been telling from the beginning, AC parameters can be estimated from DC characteristics by taking change. And the fact of the matter is, AC parameters is less than or equal to DC parameters for any device in the world. All the AC parameters approximate less than or equal to DC parameters. The best example is HFE is a AC gain, beta is a DC gain, AC gain is less than or equal to DC gain. That means small HFE less than or equal to beta there. And this how I am always encouraging people to calculate H parameters right from the characteristics. Good. Now let me take you to input characteristics. How it's behaving for input. Common base can even affect signal source at the input because input impedance is less. If you don't take care about the loading effect, it can go on affecting, and finally it can affect the signal source itself. But what is the equation for input characteristics? Vi is function of Ii comma V naught. That's input equation. Why I have taken this equation is to tell you what to take on x-axis. Normally, most of the books they are taking voltage on the x-axis. But if you take voltage on x-axis, it is given indication that that's an independent variable. But if you see the characteristics here, Ia is independent variable. Therefore, we need to take input current as independent, that is on x-axis. From our childhood, we know x is always independent, y is a dependent because y is function of x. And therefore, you always take x, whichever is independent on x-axis, and then dependent on y-axis. And some people are arguing, saying if you take voltage on the x-axis, you can see how the diode is behaving, you can understand. That's true. I agree for it. Because in input, at input side of a transistor, it behaves like a forward biased diode because input of transistor is forward biased. We take input current on the x-axis, voltage on y-axis. And if we draw this, it is behaving like a forward diode. That's why 0.6 it starts. It's almost constant. VCB1 and VCB2. And when you look at this, there is see why there is decreasing here. As we already said, that is early effect. As VCB is increasing, input voltage is decreasing. That's a fact. That's why as VCB is increasing, input voltage is decreasing. That's the first thing what we call. Similarly, if you see the output characteristics also, you can understand. In output, you know what happened? As VCB is increasing, for the same current, it is slightly up. It seems to be almost constant, but slightly up. That slight increase is creating the output impedance. So everything is explained with early effect. Now, in active region, generally, Ri is change in voltage by change in current. If I take change in voltage is very less, that's why less by high. Change in current is very high, therefore less by high is very, very small. That's why I have been telling from the beginning, input impedance of a common base is very, very less. How to bias? There are 4 ways to bias: forward, forward, input and output, forward, reverse, reverse, forward, reverse, reverse. This is called saturation region, active region, inverse active or cutoff. This is on switch, amplifier, attenuator and off switch, because maximum current is flowing on switch, no current is flowing off switch. Active region, amplifier. Opposite to active is called attenuator, because opposite to gain is attenuation. Now what are the conclusions I can give for common base? Active region is starting from 0, because you have seen from the characteristics like here, the active region is starting from 0. Then second point, CB has the largest voltage gain because Ri is very less. See, voltage gain is V0 by Vi, R0 into RL, II into Ri, Ai RL by Ri. As Ri is very low, voltage gain is high. So now look at this point. If this is very low, RL should be at least less, so that voltage gain may be limited. If voltage gain is unlimitedly increasing, bandwidth decrease, because gain bandwidth product is approximately constant. I am saying approximately constant because it's constant only for short circuit amplifier. For all other things, it's approximately constant. Anyway, that I will be discussing when I go to amplifiers. So RL of CB should be very small compared to CE and HCl. And even when the gain is increasing, you know what happens? Input will become very small. Even for small values, it will go to saturation. That's so called signal handling capacity. What is the signal that we can handle? That is called signal handling capacity. Fourth one, current gain is less. AI is less than or equal to 1, alpha is less. Input impedance is very small, output impedance is very high. CB is used for radio frequency because its upper cutoff frequency is very high. Well, what does it mean? Upper cutoff frequency means 1 by 2 pi RICI. When Ri is very less, what happens is cutoff increase, the bandwidth increase. Seventh point, CB is used for avoiding direct feed through in super heterodyne receiver. What I mean is, super heterodyne receiver, it is taking not only the forward path, it is also sending the reverse path. If a signal is going in the reverse path, how to stop it? The best is common base, because common base is the best unilateral amplifier. That's why it is used in that purpose also. So therefore, applications are, it is used for radio frequency applications and best unilateral amplifier, that is called cascode amplifier. Therefore, though CB is a very good switch but never used because of low input impedance. All the good things and greater things are minimized, are neglected when it is talked to be low impedance. Low impedance is at the input side. Now let's go for common emitter, second one. This is most important and frequently encountered transistor configuration because it is desirable to use small base current rather than large emitter current. Please understand here. In common emitter, the input becomes base. When the input is base current is microamperes. Microamperes, you can really bear it. Whereas in common base, what happens? Emitter comes into picture. Emitter current is very large. Therefore, right at the beginning level, common emitter has less input current. That's why it is preferred. Now look at the characteristics here. CB, emitter is common, forward bias, reverse bias. Then this NPN transistor, P to P, N to P. This is reverse, this is forward. Now when you talk about RB and IB, IC here. Therefore, what is the characteristic equation here? VBE function of IB VCE. IC function of IB VCE. This is the characteristics here. The one point you must observe now. In common emitter, we have taken VBE, base to emitter. This is collector to emitter. Base to emitter, collector to emitter. These are the things. Whereas if you take common base, you will have emitter to base. That is the meaning, emitter to base. So once you get the characteristics equations, you can go for the characteristics. We see here, I see here. Saturation is going almost up to 0.2. And you see the curve there, slightly up. This is base current 10 micro, 20 micro. This is 1 milli, 2 milli. If you really calculate change in voltage by change in current at IB is equal to constant, that means take 1. Change in the current is increasing. When the change in the current is increasing, automatically resistance will decrease. That's why 100 kilo decrease it to 10 kilo. Then if you go for input characteristics, it's almost similar to that. IB and VB here, it's not flat, it is slightly up. And when you're increasing, this is increasing. Now the point is, take input impedance, take VCE constant, change in VI by change in II, that is called change in VI by change in II, and change in VB is increasing now, therefore input impedance get increased. That's why from common base, from 10 ohms it is increased to 1 kilo. In fact, this is called HIE when you go to H parameters, and this is called 1 by HOE when you go to H parameters. Therefore, we can get the impedances and H parameters right from the DC characteristics. Now let me go to conclusions. Conclusion of common emitter. Input impedance is 1 kilo, output is 10 kilo. Its audio frequency amplifier, because its bandwidth is not very high, saturation approaches into active. Because into active region it is encroaching. As I said, it's going up to 0.2. It has a medium voltage gain. It has a medium current gain. That is, current gain is increased from 1 to 50 to 500. Please understand, the current gain alpha beta is always a range, not a fixed value. Then, comparison of common base, common emitter, common collector. Look at the characteristics here. Please look at the characteristics. The colors also are maintained there. Red is CB, green is CE, CC blue. But one point I want to really draw from your attention. As you go from common base to common emitter and common collector, output current is increasing. When output current is increasing, impedance will decrease. That's why this is 100 kilo, decrease it to 10 kilo, decrease it to 10 ohms. In here, the same type of characteristics, only thing is instead of change in current, this is change in voltage. That's why this impedance will go on increasing, this impedance will go on decreasing. One simple thought I wanted to carry, as you go from common base to common collector, current is increasing, and when the current is increasing, resistance is decreasing. So 100 kilo, 10 kilo, 10 ohms. Here voltage is increasing, therefore resistance is increasing. So 10 ohms to 1 kilo, 1 kilo to 100 kilo. What a simple thought I tried to maintain to you. Now look at the comparison. Common base, common emitter, common collector. As I told you just now, 100 kilo became 10 kilo and 10 ohms. 10 ohms is increased to 1 kilo and hundreds of kilo. Current gain is less than or equal to 1, beta is medium, gamma is 1 plus beta high. Voltage gain is very high, medium, less than or voltage gain is less than or equal to 1. Phase shift is 0 here, 180 here, 0. And what's application? It's a unilateral, that's called CE followed by CB, called cascade amplifier. It is inverter and amplifier, buffer and impedance matching. So what happens is, voltage gain common base is greater than, as you see here, voltage gain of common base is greater than, common emitter is greater than common collector. If forward voltage gain is greater, reverse voltage gain should be how much? Very small. If the reverse gain is very small, how do you expect? In the reverse, very small means the best unilateral. Therefore, every device is unilateral, but common base is much more unilateral. If you want to use unilateral switch, the best thing that you can go, that's what exactly happened. To avoid the reverse path in superhetad and receiver, people go for CE followed by CB. That's called cascade connection. Now, let me talk to you about phase shift for some time. See, phase shift is generally output by input. and these are the two negative signs, so 0 phase shift. You see these two. And common emitter also, if you see minus IB, minus IC by I naught, minus coming, that's why 180. Common collector, both are plus, so it is 0. Same direction, positive. So therefore, phase shift occurs only in common emitter. Now, how should I conclude the configurations? Let me talk to you about 3 aspects, because for anything to be an amplifier, 3 aspects are important. Please don't take only one aspect. Don't say gain is high, it is good. There are 3 aspects. One is gain to be high, input impedance, output impedance. So in common base, input impedance is low, but we want high. Output impedance is, we have seen high, but we want low, so it's bad. Whereas in common emitter, both are all are medium. And in common collector, gain should be more, but it's less than or equal to 1. Input impedance is high, is good. Output impedance should be low, it's good. So impedances are good, gain is bad. Impedances are bad, gain is good. So in common collector, impedances are good, gain is bad. In common base, gain is good, impedances are bad. Whereas in common emitter, all are medium. That's why it is generally preferred always. Therefore, common emitter is generally preferred and it is taken by default. So tomorrow anybody asks you, bring the switch, we take common emitter. If anybody asks you for bring the amplifier, we take it common emitter. So by default, we are going to take common emitter in general. Now let me talk to you a slight idea about voltage amplifier without keeping you for a long time till you go to amplifiers. Because this is going to decide, the characteristics is going to decide which one is better. Now voltage amplifier is what? Vi is proportional to V naught. Therefore output is V naught, input is also Vi. So 2 voltages. It takes voltage, produce voltage. If the input is voltage, source should be voltage, no? A voltage source should have internal resistance Rs. This also voltage source should have internal resistance Rs. But what is the biggest challenge for us? How to achieve the maximum output? Maximum output comes only when Vi is proportional there. For a best amplifier, Vi should be approximately Vs. Vi should be approximately Vs. That's possible only when Ri is very, very high. V naught should be very large. That's only possible when R naught is low. Therefore, Ri should be high, R naught should be low. Of course, voltage gain should be high. So Ri should be high, R naught should be low, and voltage gain high. That's the best characteristics we expect to be an amplifier. So according to that conditions, we understand common base is good in gain but bad in impedances. Common collector is good in impedances and bad in gain, but common emitter is medium. Though it is medium, it is good in all aspects. That's taken. If you really compare BJT, FET versus op-amp. So far, I have compared 3 configurations of BJT. Now I am comparing 3 devices of electronics. So Ri is low, R naught is high. High and low, high and high. So therefore, what happens here? These are the failures. This is good. That's why red for failure, green is good. So impedances are bad, gain is good. Impedance are good, gain is bad. You know why? Why the input impedance is low? Because input is forward biased. Why output impedance is high? Because output is reverse biased. Whereas in FET, input impedance is reverse biased, that's why it's high. Output is low because no bias, it is simply a channel. Whereas in op-amp, high and high. Therefore, only in op-amp we have got all the 3 characteristics. That's why op-amp is supposed to be the best amplifier. So please understand, common base has 3 configuration in which we took CE as the best option. In 3 devices, op-amp is best voltage amplifier. Therefore, we are going to take CE as a default. Let's go to some illustrative examples that will illustrate the concept which we studied. If you think that there is anything missing or if I have to add anything, we will be going for these problems. Problem 1. What are the conclusions of early effect? Vi is function of I and V naught that talks about input characteristics. I naught is function of I and V naught output characteristics. As V naught increase, junction width increase, therefore base width decrease. And as base width decrease, I naught increase. As V naught increases, Vi decreases. These are the things that we have as a conclusions. Question 2. What is punch through and how to avoid it? As we discussed already, if V naught increases further and further, base width decreases further and further. At one point, base width becomes 0, that's called punch through. To avoid the punch through, that means to avoid the breakdown voltage, we should take the lesser. How much lesser? VCC should be less than BVCO by 2 and VC less than VC by 2. Therefore, VC 1/4 of BVCO. If you take this condition, VC is less than or equal to BVCO by 2, you are sure that the punch through or breakdown will never occur. Question 3. How early effect affects the output characteristics? Let me explain. Because if you see the characteristics here, particularly in common emitter, you see there is up. Now what do you understand here? In active region, as the output voltage increase, output current increase. So this rise on the curve is because of early effect. Because we said in the early effect, as output voltage increase, output current should increase. That is proved in this portion of curve. That's why it is called early effect. Question number 4. What is the effect of early effect on input characteristics? What is happening on input? Look at here. As VB is function of IB and VC, as output voltage increases, base width decreases. In fact, as base width decrease, input current increase and thereby output current also increase. So this is the effect of early effect based on what you call input equation, input side. How many regions of BJT? Totally there are 2 junctions available. Each junction can be forward or reverse. Therefore, 2 power 2 is 4. There are 4 possibilities. Forward and forward is called saturation. Forward and reverse is called active. Reverse and forward is called inverse active or invert. And reverse is called cutoff. Therefore, there are 4 possibilities and 4 regions of operation. It's not 3 as some people think. 6th one. A transistor has a maximum power dissipation limit of 300 milliwatts for ambient temperature of 25 degrees Celsius. If the allowable junction temperature is 175, then what is the limit of the device in ambient temperature of 55 degrees Celsius? His options are 120 milliwatts, 240 milliwatts, 300 milliwatts and 360. This is in IES 2009 EEE. So please understand, in EEE also they are asking these questions and follow that. Now what is basically this question all about? It is talking about power dissipation. As the temperature is available on the collector, it has to dissipate. Therefore, Tj is called junction temperature, Ta is called ambient temperature. So actually speaking, PD is proportional to Tj minus Ta. That proportionality constant is called 1 by R. That R is resistance or thermal resistance, we call it. Some people call capital theta, some people call R. Now what is R here? PD. This. So Tj minus Ta by PD here, 175 minus 25 by PD. PD is given as 300. So 175 minus 25 is 150. 150 by 300 is 0.5 degrees Celsius for milliwatt. What I am trying to say, this is the resistance, thermal resistance. And thermal resistance is fixed for a given device. They don't change it. Therefore, this value I am going to use once again here. So for the new power dissipation, 175 minus 55 by 0.5. So 125.5, 240 milliwatts. So this is what is happening here. The option is B. Let's go to problem number 7. In a common collector amplifier, the voltage gain is constant, less than 1, varies with input voltage, varies with output voltage. It's again triple E question. Yes. Answer is less than or equal to 1 because we already gave in the concept. Therefore, option is B. 8th question. Assert and reason. Be alert now. The short circuit current gain of a bipolar junction transistor in common base configuration increases with increase in the reverse bias. See what you mean by short circuit current, that too particularly in common base alpha. Alpha increases with reverse bias naturally, because as output increases, output voltage increases, base width decrease, therefore output current increase. When output current increase, automatically alpha increase. That's one of the good things about early effect. Then reason. With increases in reverse bias collector to base voltage, the effective base width is decreasing. That's correct. Base width decreases. Therefore, both are true. But the question is, are they linked or not linked? The option is both are linked. Therefore, option is A. So, this is interlinked problem and both are linked. Question number 9. A bipolar junction transistor has high gain. That's okay. High emitter efficiency, high speed. Bipolar junction transistor has high gain, high emitter efficiency, high speed. It's a very good advantage of bipolar junction. The transistor has heavy emitter doping and narrow base width. So this is also true. But the question is it linked or unlinked? Because the AB's, the options will not change. The options are always same. But only thing is question is changing. So the option is A. You know why? Because base width is lightly doped, they can easily recombination decrease, efficiency got increased. And base width is less, therefore they can easily go. So everything linked to the base. Because base doping is less, efficiency increased. Efficiency nothing but current gain. And because the doping is less, recombination is less in the base, current is increased. Therefore, both are linked here. That is problem number 9. Let's go to 10. The early effect in a bipolar junction transistor is caused by fast turn off, fast turn on, large collector base reverse bias and large emitter base forward. As we have discussed a lot on early effect today, the answer option is C. And all that I have mentioned here, they're asked almost 3 times the same question is come. Therefore, option is C. Early effect is linked to output collector current, collector voltage. Option is C. Let's go to work out examples. We want to give you some more examples to understand this. First question. In a junction transistor, biased operation of emitter current IE and a collector current IC, then the transconductance is given by. So transconductance is given by which option here? Generally, transconductance is given by IE by GM, IE by VT. So Q into IE by VT. What is KT by Q? KT by Q is basically VT. That's why I said VT by IE by VT. So now what will happen? As in a transistor, the transconductance depends on IE, and hence where that is alpha is the current gain. So you can take alpha Q VT, KT by Q is called VT and IE. So transconductance based upon the current gain. So option is B. What is B here? The equation Q IE by KT. Because if alpha is 1, you can say, as you already know, alpha is less than or equal to 1. Therefore, this is simply saying GM is I by VT. Normally, GM is current by voltage, no. That is, so QIE, or simply you can say IE by VT. So, let them say options given. They can as well say IE by VT, that is nothing but KT by Q. So, this is the option we have. Option is B for conductance. Problem 2. Early effect in the modulation of effective base width. Emitter voltage, emitter current, collector voltage, junction temperature. The option is collector voltage. Collector voltage is the option here. So option is C. Early effect in BJT refers to avalanche breakdown, thermal runaway, or base narrowing, GNR breakdown. What is the current? Option is base narrowing. So option is C. C is the option. Fourth question. A bipolar junction transistor has a common base forward short circuit current gain alpha 0.99. Its emitter forward current short circuit gain will be, that means common emitter means beta. So he is asking from common base means alpha, common emitter means beta. He is asking beta in terms of alpha. Therefore beta is alpha by 1 minus alpha, 0.99 by 1 minus 0.9 is 99. So option is B here. Problem 5. Which of the following statements is correct? The correct set of transistor characteristics that enables to be directly determined from the slope. Is it a common emitter output or transfer? Common base input or common base transfer? Because slope means transfer, therefore its general is common base. Please remember, common base is a best reference to understand. That's why I said one word. Common base is good to understand, but common emitter is good to use. Because common base, though it is very good in understanding and so many qualities, because of the input impedance less, it has become a problem. So we still take it as common base is to understand, the best way to understand. Therefore, the option is D here. Common base. Question number 6. A typical common base output characteristics of a bipolar junction transistor remains almost parallel to voltage axis, but shows very little increase in current with the increase in output. That's true. Just now, because of early effect, I have shown it's almost constant but slightly up. You have seen the characteristics. Is it true? Reason: the short circuit common base current alpha bipolar transistor increases with increase in temperature. That's also true. But the point is, the reason is true and asset is true, but they are not linked. That's why option is not A, but it is B, because both are true. R is not the correct explanation of A. That's why these two statements are independently true. We need to say option is B. Option is B here. Problem 7. The collector emitter levels for a transistor with a common base DC current gain 0.99 and a base of 20 microamperes respectively. The collector emitter levels for a transistor with common base DC current gain 0.99 and a base of 20. What is the respective values? We need to get the collector emitter levels of a transistor. Okay, what are the values? Collector level, emitter levels from the value of 0.9 and 20 base. Okay, what exactly I mean? Very simple. You have to calculate beta because alpha is anyway there. From there you will calculate IB and IC. Look at here, you know the characteristics. Alpha is 0.99, IB is 20. So emitter current is IC plus IE. What is collector current? Beta times of IB. Beta is, if we take beta, alpha by 1 minus alpha into IB, you will get 1.99. So 1.98, if you add this 20, you will get 1.98. 20 micro means 0.02 milli, therefore it is 2. So from alpha we get beta. From beta, IC equal to beta times of IB, we get IC. That IC and that IB, if we add, IE will come. So that's the whole idea, and option is C there. If you see once again, if you want to say, I'll show you. Option is 1.98 and 2 milli. Problem 8. The phenomenon known as early effect in a bipolar transistor refers to reduction of effective base width caused by, is it electron hole recombination at base, or reverse bias of the base collector junction, the forward bias of emitter junction, the early removal of storage. This is nothing, this is nowhere linked to the early effect. This is linked to switching, that we'll see later. But let us see the answer. Early effect is basically depending on base collector junction voltage. Therefore, option is B. Option is B. Problem 9. In a BJT, ICO, that means ICBO is 2 micro. Normally, ICBO is greater than ICO slightly, but sometimes we take equal. Alpha is given, then what is calculate ICEO? Options are given. And the equation known to us, ICEO is ICBO by 1 minus alpha. 2 into 10 power minus 6 by 1 minus 0.99 is approximately 200 microamperes. 200 microamperes. Therefore, option is D. Last question. The maximum junction temperature of a transistor is 150 degrees and the ambient temperature, that means room temperature, is 25. If the total thermal impedance or the resistance is called 1 degree Celsius per watt, what is the maximum power dissipation? Power dissipation, just now we said Tj minus Ta by R. Therefore, power dissipation is Tj minus Ta by R, 150 minus 25 by 1, that is 125 watts. Therefore, the option is C. Option is C. That's all.